Okay, YouTube, in our last video, we looked at the essentials when it comes to solving exponential equations. What I'd like to do is actually use those basics of solving exponential equations to look at an application where we might want to solve for an exponent. So you notice here it says that an important application of exponential equations is Newton's law of cooling. And you can see this law of cooling here, but to kind of read through what these variables are, it says that this law states that for a cooling substance, with an initial temperature of T naught or T0. We would say that this is its initial temperature denoted by the subscript 0 to denote at time 0. So our initial temperature at time 0 is T sub 0. We say that the temperature T after T lowercase minutes can be modeled by this right here, where T sub R, or subscript R, is the surrounding temperature and R is the cooling rate of the substance. So it seems that we have a lot of variables here, and I think that the very first thing we always want to do is recognize what it is that we're looking at here. We're saying that the temperature of a substance, okay, can be told to us as a function of time. That is to say, if I know how much longer it is after I, kind of heated it up, then I know that kind of its temperature, what it'll be by using this model. And so what we're going to do is look at, a real life application problem here and talk about why we would have to use exponential equation solving techniques in this particular problem. So it says you're cooking, I guess you would call this alicha. It's an Ethiopian stew. So when you take it off the stove, it says that its temperature is 212 degrees Fahrenheit. The room temperature is 70 degrees Fahrenheit, and the cooling rate of the stew is about 4.6%, or as a decimal, of course, we call that 0.046. So what we want to do here is find how long it'll take to cool the stew to a serving temperature of 100 degrees Fahrenheit. So it looks like we have all of these values here. We have a cooling rate. It looks like we have some different temperatures F here. I think that the most important thing we do is just go ahead and start by saying, well, with this model that I don't know much about, let's go ahead and write down the things that are known to us. And so it says when we take it off the stove, its temperature is 212 degrees. And so I suppose we could refer to this 212 degrees as being its initial temperature. And so T sub 0, which is our initial temperature here, we'll go ahead and write 212 degrees Fahrenheit. And we'll just make a little note here. This is our initial temp. So initial temp. Now, what else do we know here? It looks like it says the room temperature is 70 degrees Fahrenheit, and we were to use T sub R for this. So let me get this in red also. We say T subscript R is 70 degrees, and this is in Fahrenheit as well. So we say room or surrounding temperature. So we're going to say room temp. Okay, so moving onward, it says that the cooling rate of the stew is R here. We see that R is 0.046, and we're going to make a little note here. This is our cooling rate, okay? And it looks like it wants to know how long it will take to cool the stew to a serving temperature of 100 degrees Fahrenheit. So here's the deal. When it comes to our model up here, what we're looking for is how long it's going to take to cool the stew. So in terms of the thing we want to find, it looks like the one thing we want to look for here is time. So we're going to say that our unknown here, unknown, is time, and we want to know what this is. We'll say time. But what we see here is that our last known is this 100 degrees Fahrenheit, and what it says is how long will it take to cool this to 100 degrees Fahrenheit. Well, if that's not the room temperature, and that's not our initial temperature, where would we put this in? Well, what we're saying is we're going to put this in for the value of our function. We're going to put it in here for our temperature at a given time, and what we're going to do is work backwards to solve for, well, what would that time have to be in order for this to be the temperature? So our overall temperature at a given time is 100 degrees Fahrenheit. So we're going to make a little note here. This is a temp at time t, which is the thing that we're solving for here. So looking at this model here, we have this t equals the difference of our initial temperature and the room temperature multiplied by e to the power of negative rate times time plus t sub r. What we could see is that the things that are known here, this room temperature, we know E, okay, we know the initial temperature, we know what temperature we want it to be, we actually even know the rate. The only thing that is unknown here is the time. And so you can see that with where this time lies in the exponent, we're going to have to use our strategies for solving an exponential equation here to solve this. So let's go ahead and do this. Let's go ahead and plug in all of our knowns for this model initially. So we'd say that our initial temperature minus the room temperature, this is E to the negative R times time, okay, plus T sub R. So putting all of these things in, these values, we'd say 100 degrees Fahrenheit is what we want the temperature to be. Our initial temperature, okay, was 212 degrees Fahrenheit, and we say that the room temperature is 70 degrees Fahrenheit. where our rate, we'll go ahead and plug in our rate up here, and then it looks like this room temperature, again, we have to add that on as a constant. So what I'm going to do is I'm going to simplify here. Simplify first, okay? And this simplification looks like we don't have much to do with the left side. We say that's 100. But inside the parentheses here, 212 minus 70, let's go ahead and find that difference. So we'd say 212 minus 70 gives us a difference of 142. So we say 142 e to the negative 0.046 times time plus our constant 70. So now, this is simplified as we're going to get it. What I want us to notice here is this. In terms of an exponential expression, it looks like we have only one base. In our last video, what we said was, well, if you have more than one base, try to drop one of them on each side, and we could use the one-to-one property of equality, this thing that says b to the x equals b to the y if and only if x is y, or their exponents are equal. Well, because we only have one base, what we're going to have to do is this. We're going to have to isolate that base, and then we're going to use logarithms or inverses of exponential things to undo it. So in terms of isolating the base, this is the first equation we've actually looked at where we have to do this work on our own. So that is to say that if we're going to isolate e, make a little note here, isolate the base e, the base e. What we're going to need to do first is kind of like solving a normal equation. I guess by normal, I'm saying that everything up until now, you know, if I would have said go solve this, everybody says, well, you got to get rid of the 7, you got to divide by 142. We're really going to do a lot of similar things here. So starting with this, we're going to go ahead and start by subtracting 70 from both sides. So you're going to want to undo your addition and subtraction first. So we end up with 30 equals 142 e to the negative 0.046t. Now the next move to get e to the power of by itself is we're going to divide both sides by 142. Now, here's the best advice I can give you. When you're solving exponential equations, go ahead and use fractions over decimals here. And so at least I'm going to go ahead and reduce these. I notice they're both factors, they both have a factor of 2. So 15 here, half of this would be 71. We could say that this is 15 71sts is equal to e to the power of negative 0.046t. Now, the reason why we keep this as a fraction is because it allows us to use exact values instead of decimal approximations. So now that we have isolated this base, what we're going to see here is this. Because I cannot easily write 15 71st as a power of b, we're just going to take a logarithm of both sides. And the thing here is we have to take the log base e of both sides. So really quickly, let's remember this. Log base e of x is the same thing as the ln of x. These are the same things. So what I'm going to do is I'm going to take the ln of everything on the left and set it equal to the ln of everything on the right. And everything we had on the left here was this 15 71st. Everything we had on the right was this e to the negative 0.046t. So the thing here is that when we take a logarithm of an exponential thing and they have the same bases, they cancel out. And so what we end up with here is this. We get this expression or this equation. The natural log of 15 71st is actually equal to negative 0.046t. So the fabulous thing about this is we can just go ahead and divide both sides by a negative 0.046. And we could say, well, then that's going to be the time that it takes for us to reach an initial temperature of 100 degrees. Or not initial temperature, but a temperature of 100 degrees. So first things first, let's go ahead and write this here. We say that the time itself is the ln of 15 71st divided by negative 0.046. This is the time, and by the way, it's in minutes. But what we want to get here is a decimal. So with our calculators, let's go ahead and do this. We're just going to clear all this out. We say that the ln, or the natural log of 15 divided by 71, in parentheses, divided by a negative 0.046, is a time of 33.796. We'll go 33.8. So approximately 33.8 minutes later, we would go from being 212 degrees to being only about 100 if the room temperature is 70 degrees Fahrenheit and if this is our decay rate. So this is a really good example of writing down what you know with these expanded models that you'll see from time to time, plugging them in and looking for what you don't know, and then just using what you know about solving equations to go from there. Cheers.